Hello. Random Sunday stream. Nothing special today, just cleaning the code. And maybe preparing to implement some features, starting in 1 minute roughly. One moment. Alright. We prepared the stand firmware last stream and it's printed and tested. It looks kinda nice. Though I would imagine that motor angle should be a bit different because the rotating thing is not visible that much. But I will fix it later, I guess. So now, cleaning up then. Last stream, actually a stream before last, we were doing encoder. And we implemented the structure, we implemented the handling, all we needed. Actually, encoder has more things that needs to be added. We will return to this when we will work on position control loop. But position control loop is way in the future, so we will not think about it now, but we will have a problem that we need to somehow calculate the position in float value accurately within many revolutions. I have ideas how to do it better-ish, but we will handle it when it comes to it, because now it's not that easy to do. So let's open the build that builds examples and see what we have to work on. I think the last time I worked on those, which was quite a long time ago, I left quite a bit of things first not removed from this file, but also not implemented in this file. So there's quite a lot of cleanup work, and let's do it. First, let's see what we have in this file. Because actually this project started a year ago. I worked on this for a month, then I got busy with other stuff, and I came back to the project a year after, which is now, and I'm saying we, like I have to now remember what I was doing and clean these things up before I can move forward. And let's do it. So the example is correct. There is an unimplemented input example, but we will not implement it yet because we don't have anything to test it with. Those are encoder examples. We were struggling with them for quite a while last streams, but they are functional. We've tested it and confirmed it. This one, actually, let's run it. Let's run it and see if it works properly. This is 5. Yes. Is it though? No, it is not. Is my numbering incorrect in main? It is. The hell? Oh. Oh, hello. We're not supposed to be here. Alright. So where are you supposed to be? Is this a valuable example? It is, because it is a bring up file, so we have to have all the functionality one by one to bring every hardware element on the PCB up, which means test if it's working. So this is a valuable example. We just need to rename it properly. And yeah, I think it's just a naming problem, because the name explains what we want to do with this. I did. Thank you for joining up. I thought that maybe more people will have the same question. So this is the reason I created the document. And I hope it was decently written. I'm not sure. And I hope you will find it useful. And I will try to do something similar if other people will have like similar questions. Oh, you did? Right. Should I be expecting to blow up soon? Thank you, thank you. Thank you so much. Like, was it good enough for sharing? Because like, what if it's bad and like people will come here to just throw eggs at me? That will be awkward. So, right. This seems proper. I hope so. This seems alright as well. Let's just double check what frequency I use in the app. Oh, I don't use any. What the hell? Oh, I see. It makes sense because this is the code that is already closed in the function here. What? Only 2 millions? Okay. 2 millions for SPI is rather small. I don't remember why I selected 2 millions. I think I had a reason. I'm not sure because SPI can go up to 10 million, 10 megahertz meaning, and 2 million is on a very low side. On the other hand, the driver we use from Texas Instruments, which is DRV8320S, doesn't need to be communicated to using SPI after it's set up. So this might as well be 10. And as long as we run it at the startup, it should be fine. So I will leave it as is. So now let's go back to the examples and see the rest of the code. And also let's compare the rest of the code to what we have in the function. And for this, I will open the function in another perspective. Like this. Let's see. I think this is an important part because we don't want to accidentally start spinning whatever is connected to the outputs of the motor. So we might as well make sure that our PWM is set to 0 on all channels. Then we do not enable driver. Okay, that makes sense because SPI I was planning to make a YouTube with watts, but then I like watched my watts and I hate my like I hate the way I speak. I hate my accent, I'd say. And I was like, no, this is too embarrassing for now. Maybe later when I'm more confident in my speaking, I will like start uploading watts, but not for now. Thank you. So now, reset all PWMs, fine, start SPI, because SPI is considered not active when it's low, when it's high actually. When it goes low, we start the next transfer. This is a way for SPI to communicate that new message is arriving. So this is all right that we force the stop of the transfer before we start communicating. Now enable driver, that is fine. Dummy delay is also fine, but I don't like, or actually, yeah, that's all right. The comment explains as well. I think reading 0 is actually quite a terrible example because given that this is a global variable, it will always be 0. So we will not understand if it read anything at all at this point, because like even if we read 0 or we read nothing, it will still be 0. So I think it's not a very nice thing, but I see that there is another test after which should return the value, so it's fine. Okay. Oop. PWM3X, okay, because our integrated circuit has 3 modes with a single PWM input, with 3 PWM inputs, and with 6 PWM inputs. 6 are needed when you want to control the dead times yourself, but I don't want to control dead times myself because this IC has actually a very nice feature of it's controlling dead times automatically based on measurements, internal measurements, and this is like very nice. And forcing dead times is not something you should do unless you really understand what you're doing. So time delay of 1 is awkward, but okay. I don't remember why is it needed, but maybe it like I have hope that my past self was actually a reasonable person and did this for a reason, so I will not complain for now. Also, I watched a video by Artful Bytes, and he said using command line workflow is better than vendor IDEs. Do we discuss it in guide? You personally use both? I actually disagree a bit. That depends. There is a very good point for using command line, and actually it should be somewhat of a goal you should strive to, but it must not be a criteria. It might not be a requirement because, for example, you can work very successfully for a very long time with STM32 without using any command lines at all. The point for command lines is, for example, when you want to start building your project with CMake, which is a big deal because, for example, it will be much easier to implement GitHub Actions or stuff and do the hardware in a loop testing. When you, for example, push a commit to GitHub, then it automatically downloads like everything to your test computer, which like builds the code, tests the code, and flashes it to the device, then tests it using another device, and then like returns the build results, which is a very complicated workflow to do and very advanced. So I wouldn't say that this is something of a requirement for a beginner. Like I wouldn't say it's a requirement for like a middle level developer, like at all. So there is a merit depending on what you work with, but this is not a requirement. Like for example, working with STM IDE, like kubeiDE, is like more than fine, especially for the beginners. Because when you are a beginner, if you will force too many things on yourself to learn, you will never learn anything because it will be like information overflow. So just start with ready-to-use tools and focus on learning STM32 itself. And then when you're confident with your programming skills, you can like go and start learning like additional stuff, for example, like CI/CD, like GitHub, for sure you need to learn. Actually, I should probably add it to the... I definitely need to edit. Let me note it for myself. Oh. All right. Some notes. Like learn things one at a time, because if you will force yourself to learn everything at once, you will like it will be very hard. Like you will struggle a lot. Because like embedded development is not easy, especially in the beginning, and it's not easy later as well, as I wrote in the guide. So pace yourself. Like it's nice to say that yes, you need to know everything when you are like 10 years of experience and like know everything already, and you think, oh, these newcomers, they don't know anything. But no, like when you're a newcomer, it's very hard to learn. And I know from experience because I was an educator, so like I did teach people how to like learn this, and I saw the struggles. Like it's not easy. Okay, let me note it for myself, and let me note for myself to make sure that my Obsidian is not opened on stream next time. Done. Let's get back to our example. So now, this register should return 32. Okay, we will test this. Another delay, all right. And this returns that. Okay, this is self-explanatory, quite decently written. Let's test it. And to do so, here looks fine. This node is not needed. Nothing here. Let's flash it. Oh, why? Oh, I see. I didn't connect the debugger. Do you like how the stand works that I developed in the previous stream? Or like, is it off? Like, I don't really like the angle the motor looks at. I think it should be a bit lower, at least for my camera angle. I see, makes sense. I renamed this. How could you? I tried so hard. Like, it should look nice. And now I can actually show the board properly. Like, for example, you can see like the MCU. And I also need to like remove this like the light. And you can see like all the dust in my room around my MCU and all the parts. Like in case I need to show something. Quite handy, quite handy. This counts. Okay, let's try again. All right. I see, makes sense. Let's put it again. It's built now. Let's flash it. So now, let's go to the lab expressions, and we have nothing useful here. Let's remove all the things I've tested off stream, add this back, and add our debug files. Not files, but arrays. Oh, I see. That makes sense because like the video stream is quite static. The motor rotates only in a small fraction, and like it's only rotates, so it's not exciting at all. So I would imagine people not paying much attention. I think I should show the motor more and show the PCB only when asked. Maybe, I'm not sure. Like, I will need to figure it out later. But for now, it is how it is. Okay, that doesn't seem to work. Okay. Oh, I see. Makes sense. Okay, this test works. Communication works. We confirmed everything, and this 5 million. Okay, let's it be so. I don't mind at all. Oh, I remember now. I remember why I put 2 millions, because for whatever reason the... Oh, I do remember. It's an electronics issue. Because of my tracing of the PCB, I imagine the SPI lines had very terrible signal shape, so I had to lower the communication speed so that the signal has proper shape that can be recognized by the IC. And this is the reason I use lower frequency, but like it's not a big deal for the motor driver because we need to initialize it before we start rotating, and after that we don't like communicate it anymore. So should be all right. Okay, this test is ready. It works. Let's continue implementing. Bring up controls. So what did I mean by that? I think we should try to spin something. Let's do it then. And for that, let's actually copy this code as well. Okay, 3 mode. This is fine. I don't remember what this is, but I think I was smart enough to figure it out beforehand, so I will trust myself in the past. Or I will spend 2 hours debugging issues, which is also possible. We will see. Where the hell am I? It is supposed to be a pointer. So it is supposed to be an address. Okay. And this is fine as well. So we set everything up, but microcontroller is not initialized by this point, so we need to also add all these. What else? Peripherals as well, but they are set up. Looks good to me. And at this point, we need to do something to rotate the motor. They have a feature to rotate the motor in open loop, so it's very easy. We don't need any feedback, any sensors, anything at all. So it's actually more of a PWM test and PWM implementation rather than the IC test. Or maybe it's partially an IC test as well, given that we need to test if the motor spins and if transistors of the driver opens up like as we expect. I will need to write the description. But later, now. And what I wanted to note, not much, I guess. I guess we just need to implement it. And for that, we will need our favorite dummy delay. Let's simulate 10 kilohertz, I guess. And 10 kilohertz is 100 milliseconds. So, right? No, wait, it's 100 microseconds. Wait a second, am I an idiot? No, I'm not. That's correct. Like, maybe I am, but not in this particular case. Okay. Oh, hello, Negorsa. Welcome back, welcome back. How are you doing? I have 2 regular chatters on my stream. I'm so happy. So now we need to start spinning a motor. Spinning like we mean it. Let's do it. We need to drive our transistors, but before that we need to let them know what exactly they are driving. Do I have any variables for this? I don't think so. Not a big problem, not a big problem. Given that these are bring up tests, let's make them as static. That will be more confined. Okay, let's stay angle. Always initialize your variables with F. Actually, Nigorsa, do you remember the last stream you were on? I was struggling with performance of angle calculations. Are you curious to know how I solved it? Because like it was quite a messy bag. I knew the issue that happened. I just didn't get the same issue for a long time and I forgot about it. So the issue is actually very funny. Let me open up the file. Like, it's not funny for people who don't know this, but it was funny for me because I knew it. Like here in the formula, as you can see, a very important part, like here, there is m pi f32, and this is not an msh variable. It is a custom one, and it is a custom one that is defined as float. And if you open up the mass.h, let me do it just for the test. It is defined as double. So the issue with C compilers is that every time there is a double in the calculation, the whole calculation, unless you force this double to be float by direct type conversion, the whole function will be forced to be, like, the whole calculation will be forced to be double. And given that FPU on STM32 only works with floats, like, the whole calculation was forced to be double, like the division was double division, and like after all the operations, the double value that was a result was converted back to float value. And that was the issue. And when I moved removed this value and added my custom values from my custom definitions of math constants, it went from like 200 cycles to like 11. Actually, like, it was even less than 11. So the whole issue that I was debugging for like more than an hour, it was just a float which is double. Yeah, and also they are very frustrating when you're a beginner. Like, if I was myself like 5 years ago, I would have been like depressed for like a week probably from this bug. But given that I knew how to solve it from like past experience as well, it was more straightforward this time, but still, it can be very frustrating sometimes. It is hard to find if you don't know what you're looking for, yes, for sure. But also, yes, actually, there are some problems. For example, when you define a lot of variables, when you have like a big project, like similar to what I have now, roughly, and you like open up, for example, like this is an example file, and we open up the definitions we need, and we need like a lot of stuff. We need like encoders, motors, like everything has a struct, and you define the default values. And if somewhere here you have like a float, and you define it like this, you already add a double to float conversion to your code, and like, first of all, your flash becomes huge because conversion from float to double like takes quite a lot of like operations. Then you can force the like math to be double math, and it's like it can mess up things a lot. But there is a way. If that FPU uses more cycles and slows, if I understand. No, FPU is actually a very cool thing. FPU is the same as ALU, but for the floats. The problem we face right now is that FPU only, like on STM32, only works with float, with floating point values that are 32-bit wide. And double is a 64-bit wide floating point value. And FPU cannot handle this. So it has to like do operations outside of FPU. Actually, Negworsa, this is a good question, and I have no answer to this. I will actually note for myself to like Google it, because like this is a very good question. Yes, like it is software, like it's converts to double. It can use some like mass operations, some maybe floating point operations, but it's like a lot of shenanigans like that are very complicated to calculate the doubles and then to convert result to floats. When if the value was initially float, it would just send the whole operation to the FPU and convert it in like a single operation. And that's why it's like very important to never use double by accident in your code. And I was caught by this. So let me note your question to Google it, because like it's a very nice one, Negworsa. Is there a compiler option to stop using software double? A very nice question indeed. I would imagine for sure that there is an option if you use something like static analyzer, but I'm not sure if compilers support such things directly. It would be actually very nice. I would imagine that something like this has merit for embedded, like a lot of merit, but I'm not sure if it exists, like if something exists. We will see, we'll see. We can Google right now, if you don't mind me Googling on stream, or I can do it off stream and like tell the answer later. So where were we? Okay, let's Google, sure. Google. This is not a full question for GCC non-YABI. And GCC non-YABI is a compiler that is used for STM32 and like many ARM microcontrollers from all over the place. Yes, you can stop from using software floating point emulation. Stop using only software double. Let's see, double. Sorry for the flashbang. This is something confusing. Okay, this is very confusing. I don't think it's an answer. Compartmentalization in embedded systems. Should I ask ChatGPT? I don't know. What is this? I'm trying to figure out, should I enable soft floating point support? I'm not able to use float or double. Okay. 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 Okay, this is not very clear for me. Okay, that didn't help at all. Okay. Found out the root cause of these issues. The issues linker script file. Farm stack unwinding. Okay. Nope, that is not the answer. No. What is that? Using embedded systems. Not the question we want to ask as well. Okay, let me open my ChatGPT and make sure that I will not leak my history. Who knows what I'm talking with ChatGPT, you know? Actually, I don't talk to it a lot. Oh, I see. Sure. Okay, and let's copy our Google request. But be able to use float to still use float. Let's see. Okay. Software floating point, which means both float and double are computed in software. Okay. Yes, this is exactly what is happening. No, this is not what I want. This is what I have. Which is float is FPU and double is software. Key compiler flags. Okay, this is fine. Use hardware floating point calling convention is fine. Use FPU but keep soft ABI compatibility. I have no idea what it means. On a single precision floating hardware, this is true. Close related, yes. There is no compiler flag to make double use hardware. This is fine. This is not my question. How to effectively avoid software double? This is a question. If you go, yes, this is my question, please. F single precision constant. Oh, yes, the answer is here. Oh, this is very nice, very nice. We found the answer. So it is possible. Now let's actually Google what those flags means. ARM GCC. Let's see. There is no such flag here. Very interesting, very interesting. No such flag here as well. Hello. Are you telling me that there is a fact that I cannot Google? Is this a fact? Maybe I should do it like this. Hello? That is not helpful. That is helpful, okay. You have a warning when a value of type float is implicitly promoted to double. Oh, this is very useful. This is the exact answer to a question. Single precision float point unit, influent float in hardware, but emulated double in software. On a such machine, doing computation using double also is much more expensive because of the overhead. True. It is easy to accidentally do compilation with double. Very true as well. This is exactly the issue. Okay, this flag is for sure what we need, and let's check the second flag. This is very useful. Okay, there are quite a few of them. Thread floating point constant as single precision instead of implicitly converting them to double precision. Okay, both are very useful. So this one says that all the, like actually, if we will use this one, the second one is not needed because all the values will be treated as float. But I would imagine that adding them both to the compilation is a useful thing to do just for like style sense. So let's add both of them actually. This is very interesting indeed. So how do I actually add custom flags to the compilation? General maybe? Oh, doesn't look like this. It's assembler, compiler, okay, bugging, preprocessor, optimizations, warnings, miscellaneous, other flags. Oh, okay, hello. Let's actually test it. Like, now that you've started it, I'm curious to test it. So, it's your fault, but we will spend like half an hour doing this. Get ready. And the second one we need is this. And let's actually finish reading what ChatGPT said. That helps. True. Audit hero code. Yes, this is very true. But this is also very true. This is not very useful. Okay, the answer is fine. And let's now test it. And how we will test it? We will test it using MassPy. Applying close. Also, I would imagine I need it for all my builds, but that's fine. This is fine for now to keep it here. Just remember to edit later. Variables no. I have no idea what this means. This may be useful. I have no idea what this means. Okay, okay. Short enums. What is this interesting? Okay, apply. There is no way to copy them, so I will have to do it manually for everyone. Alright, whatever. Fine, close. So now let's test it, and we will test it in the first example, which is 0, because it's an empty function we can do anything in. And let's say, let's figure it out. No, we will not have a warning. Actually, you're correct. Let's test them one by one. Double promotion, let's remove it. And let's make sure that we will get a warning, because like we are learning this educational stream, so we might as well learn things. Fine, close. And now we're supposed to get a warning after we do something like float angle. Let's say test angle. And also let's spell correctly. And float test angle step, which let's say will be 0.05. And now let's do the math, which will be something, nothing in the main before the while. And in the while, let's say dummy delay. let's say once every 100 milliseconds. And let's say we would like to calculate the sine result. And let's say sine result equals to... Actually, let's make it... What do I even want to achieve, though? Okay, let's make it degrees, so that we have a way, like a reasonable way to use MPy. And it will be also degrees. So the step will be then, let's say, 2 degrees per step. And we also need to set up system clock, and set up debug timer, but it will be set up or enable actually. Okay, I don't remember. Let me check. I see. It's profiling. Makes sense. Enable our profiler. Copy the profiling code. To know things, we need to measure things, and measurement is very important. Let's add the variables. Timestamp 1, copy, change. Okay. So this works. What else do we need? We need to enable FPU, and FPU is enabled in the main. It is, so it's fine. What else? So ARM sine F32. And let's say, okay, let's actually do float angle radians equals angle test angle degrees divided by 360 and multiplied by MPy multiplied by 2. Actually, let's remove F from all of it just to see how many warnings we will get. This is the angle we need. And we need to measure these lines. The only thing we need to measure to profile, because sine is not what we're profiling, and we need to not forget to do. You haven't seen anything. Test angle degrees plus equals angle step. So, do you think it's working? Okay, it was good to me. For now, maybe it's not. Who knows? Let's build it. Okay, sure. Warnings. Nope. No, I got nothing. What? Did I do it correctly? Example 0. Do I run example 0? I do. And I didn't get a warning. Let me check again. MCUGC compiler. Okay, maybe I used the wrong flag. Let me double check the docs. Which flag means what? We currently use flags that treat floating point constants and single precision. Okay, this is the wrong flag. Actually, this is fine. This is a flag that's forces us to convert doubles to floats. So let's see the performance. This is actually what we want. Should be all right. Math expressions, this array, run. 4. So it is insanely fast. And now, for the experiment to be scientifically proven and correct, let's remove the flag. Apply, rebuild, apply and close, and flash again. Run and test the value. Oh, 1000! It works. It really works. So the first flag is tested. It forces values to be float points. And now let's test the second flag that is supposed to give us warning. So let's add it back. Holy, it works. It's such a nice find, such a nice question. Actually, thank you for asking it, because I learned a very useful thing that I would actually actively use. Because this is insane. 1000 when we had 4. This is 250x the performance. A clickbaitable title of I made my math functions 250 times faster. Only here on my channel. So now what is our second flag? But it's such a nice thing actually. Okay, let's edit. Let me find it. Where are you? Okay, I think I made a mistake by closing ChatGPT too early. Let me reopen it. No! Did it save? No, it did not save. Oh, it did save, but in a different place. So this should give us a warning. Let's test. Let's go back to the normal view. And let's see, let's build it. Okay, we do have a warning. Implicit conversion from float to double. We have 6 of them. Oh, it's actually catch. I had errors like this in different places. Holy. And what is double here? It's supposed to be. Oh. It hurts. It hurts. So many places where I actually use double. Such a nice find. Such a nice find indeed. Any more places I need to know about, Mr. Compiler? And what is this? That's all right. Okay, both flags are actually very useful, and I will use them actively. Let's edit, and I will note to myself to actually write them down somewhere. One moment, I'm pondering. And now let's actually test them both. Apply, rebuild, apply and close, and let's see if builds will still warn me. No, if I use both flags, the build doesn't warn me because this value is converted forcefully, which is actually I don't like it. I don't like it because it allows for mistake, and if you forget this flag, for example, if you build in CI/CD, in continuous integration, and you forget this flag, you will build with double. And this flag allows you to be lazy and to actually forget to edit. I actually only would like to leave the flag that warns me about it, because this is useful, because this forces a very nice style to your code where you are forced to use floats. And I think this is much more beneficial than silently converting them like doubles to floats. So I will actually personally only use like the first flag, because I think it's very useful. And the second flag allows you to be lazy. If it makes sense, I hope it does. Yes, actually a very good idea. This is a very nice idea, Nigwarsa, to force it in production. I actually would agree, yes, for sure. So in case like a new developer who came like 2 weeks of experience came and just push forcefully, like, because like I know that young programmers like to ignore warnings completely. So it can happen that code is flawed, can go to like production, and I would imagine that forcing it in production is a very good idea. I agree. I will note it for myself as well. Actually, then I would say it makes sense to do a warning flag for debug builds and do both flags for like only the second one then to release builds, because the warning flag will not work if the second flag exists, because every value will be forced to be float. So one flag for one situation and another flag for another situation. I think that makes most sense. This is such a nice find. I'm so happy, actually. This stream is worth it today. Let me note it for myself. Production. And the second flag for release builds. Like, the more you know, guys, the more you know. So this example went really well. I will comment it out just in case we will have other topics related to this stream, and I will remove it later. Okay. And let's flash something spinning. Like round and round we go, and let's continue working on examples. So first, let's debug you start. It is not built, okay, sure. Let's build it. Also, Nick Borsa, if you're interested, in the description of the streams, there is a link to the document that explains how to learn embedded from scratch. If you want, you can read it and give feedback. I hope it will be useful. Like, I know that you're working with RISC-V, so maybe you are already on a stage of your like skills that this guide will be useless for you, but the feedback is very appreciated. So what we were doing, we were flashing the spinning motor. Let's build it. Okay, no warnings, so I didn't make any floats conversions from double in this build, and let's flash it. Debug. And run. And we're not spinning. Why? Where are we? If you want to buy a nice MCU to work with, like, I would recommend an STM32G4 Nucleo. It should be like $20, maybe less. I'm not sure. I don't remember the prices, but it should be like decently affordable. And it has like most of the things you may need to like experiment freely. At least this is what I use actively. So like my board has G341 431. Sorry. And like, I like the G4 family a lot. It's very functional, very useful. But like, maybe you will find something else you like. It's just a recommendation. So now, why are we not running? Oh, we are running. Oh, I wasn't needed. Okay, of course we are running. We were calibrating first. That makes sense. Okay, let's go back to examples then. Remove this here. Looks fine. Sip of water. And where are our examples? It is a custom board, yes. It's designed in KiCad, and I think it was like my second board designed in KiCad. Like, I know PCB design. I was working as a PCB designer for some time. Like, not an advanced one, but like a decent one. My role was PCB design plus embedded development. It's like when you know everything but not nothing at all at the same time. So like, this is a file of the PCB. Will the 3D work? Yeah, it does work. So it looks very similar, just without test points, because test points are expensive. So you don't really want to put them on every PCB. And like, I have an unsoldered version. Okay, now that I bragged enough, let's get back to work. Examples. What is that? I will need to check it, but for now, we were working on this example. Sure, we need to finish implementing the spinning, the open loop spinning, which is almost done. We need our angle and angle increment. Which will be equals to, actually, let's define FOC open loop frequency. It will be not float, but actually it will be float. 6 MOSFETs controlled by what in the center is that doing hardware FOC or just pure MOSFET driver? It's pure MOSFET driver. FOC is implemented in software fully. So this is a driver from Texas Instruments. Does it have any? Let me change my light. Oh yeah. Actually, let me rotate. One moment. Round and around and around and around we go. Oh, where the hell am I? Okay, that is... okay, that doesn't work. One moment. So this is a MOSFET driver. Like, if you are curious, it is called DRV, like here, 8320. Just with capital letters. And it's pure MOSFET driver that supports dead times based on measurements and have 3 main ways of controlling it. You can control it with single PWM input, with 3 PWM inputs is what I do, and with 6 if you want to implement dead times in software. So FOC is fully implemented on STM32. So it will be a current loop, a position loop, like all the current measurements, like everything else. Here we measure currents on current amplifiers separately. And here are the, they are not very well seen, the current shunt resistors, like 2 of them, and external transistors, of course, capacitors, like all you need for FOC implementation. Okay. Angle increment will be in radians, so m to pi divided by open loop frequency. It will be const as well. Static Zen will be just const. And like this, and like that. Looks good to me. So here, instead of 1000, let's actually do 1 million. Enough zeros. I hate that C doesn't have a function to separate zeros, like for example, like this. It would have been such a useful feature because especially on the microcontrollers, when you, for example, set up microcontroller frequency, you need to type like 170 millions, and every time you just count the zeros. Is it correct number of zeros? Is it not correct number of zeros? Like, it's frustrating. So divided by open loop frequency. It will not be precise, but it will be good enough. So what else? We need to calculate our sine. And that does it. Do we have a test inverter here? We do. Current angle. Okay, this calculates PWM values, sets them, and then we need to update the angle. And current angle plus equals current angle, no, angle increment. Looks good to me for now. Do we need anything else? Set basis, looks fine. Let's test it. So it was example 6. Controls. Let's try. And run. Does work. Very nice, very nice. And it's 1 revolution per second. Cool. Next example. Actually, 1 revolution per second is too slow. Let's add a constant. Const float rotation. Okay, no, RPM target. Let's set it to 0.2f. It will be RPM target multiplied by this. Let's test it again. Okay, this is not RPM. False alarm. This is RPS, revolutions per second. Looks faster, I guess. I'm not sure. Should be all right. Also need to fix light. Oh. Good enough. So this example is done. Let's go next. Okay. So bring up ADCs. Okay. We haven't worked with ADCs yet. Let's do it. Why not? UART is all right, but cannot be tested by itself. One moment. Okay. Okay. I read code for myself from a year ago as if like I haven't seen it ever. I'm glad I document everything because for me personally, it's hard to remember what I was doing like a month ago. How to test, flash, okay, okay. Oh, okay, so there is an example for this. Nope. Yes, looks like this. All right, let's actually test it. Sure, why not? Okay. Let's open it in terminal. Here and there. Let's flash it. 10. This remove. We implemented this. Flash. Nothing builds as expected. Oh my. Oh, good night. Thank you for watching. Thank you for coming here. Don't forget to leave your feedback after you read the document. See you next time. This is okay. Okay. Sure. This was a useless comment, I guess. Oh, that's annoying. All right. That is very annoying. But I think I know how to fix it. Let's just copy the working code. Quick fix, quick fix. All right. And oh my god, there are so many things that don't work as expected. These functions don't even exist. Oh, okay, let's not test it today. I remember the issue because I have a custom-made debug protocol that allows you to save streams of data or buffers of data. Like streams are endless and buffers are constant length. And to implement this feature, I had to make a very custom UART setup. And this example expects a standard UART setup. So we give it that we don't run standard one. We cannot test it yet until I fix it, and fixing it is not my plan for today. Therefore, let's leave it as is, and let's remove it, and we still have errors. Okay, all right. Calm down. Unused variable, what? Oh, sure. I just renamed it. My bad, my bad. Now it works. Let's flash it again. Let's run it, and we spin. Nice. So ADCs. ADCs will be tough, because ADCs, at least for this project, are... Like, there is an interesting problem to have when you implement FOC on microcontroller. And the problem is that you almost always require to have at least 3 ADCs, like separate ones. And by a separate ADC, I mean separate peripheral. For example, in STM32, the one I use has only 2 ADCs, ADC 1 and 2. And this is not enough. And why is it not enough? Because for the perfect FOC, you would like to measure your phase currents at the same time in both channels. You don't want to measure them one by one because you will have like an error. And you will have like a lots of error for many reasons, but this one is quite a big reason for errors. So you want to measure at the same time. And like if you measure at the same time and for FOC, you would like to spend, like, let me actually draw it real quick. One moment. For FOC, you would really like to, like, for example, this is our time. And let's say like this is our period of FOC. TFOC. So it will be T1 and T2. And it will be like T2 minus T1. So in this period, like in the perfect world, when everything is how you're supposed to work, you would like to measure your ADC like the whole period. You would like to like have an average value of the whole period. And then at the very end, you would like to use it for calculations and run the next cycle. This is like a perfect world, but it's not possible. And even if it was possible, there is an issue. We have two channels, like channel 1 and 2. And they both require this behavior. So they measure at the same time and they measure as long as they can within a single period. But we also have other channels, like we have, like, for example, channel 3 and channel 4. And channel 3 measures the voltage we have on our main bus. And this is very important because voltage of the main bus decides like the PWM duration we select, because we control using voltage vectors. So we need to like measure this as well. And this measures, I believe, temperature of sorts. I don't remember which exactly temperature, but I can look it up. And the problem is we only have two ADCs and they're both busy. So this is a problem with the MCU I've selected. So the better solution would have been to have MCU with 3 ADCs. So the 2 ADCs are only working on FOC current measurements at all times. And the third ADC measures like all the unimportant channels. That would have been a best solution, but the microcontroller I selected doesn't support this. So we have what we have, and because of it, we have design shenanigans we have to take to make both work. And let's figure out how I've done it before, and let's figure out how we will do it now that we are smarter. At least I hope I'm smarter after a year of not working on this project. But first, let's find an example when ADC is used actively, which looks like this actually. Test all ADC channels. Quite a fitting name. All right, let's uncomment it. It will break in multiple places, but whatever. This is not needed. Okay, makes sense, makes sense. Makes sense, makes sense. Still makes sense. Okay, also makes sense. Current basket measurements. What is it? It is not even a function. Let's just check the file. Where would it be? I think here. So let's see what we have available. Okay, okay, okay. It is a good question. I don't think so. Actually, let's check. Let's check. Why not? Given that we are doing an educational stream today, we might as well check if it exists. So here we are. Let's see. Offers up to 3 ADCs. Okay. Let's open them all up. What body do we have? Let me double check the name on our PCB. Okay. I think I pressed something wrong. One moment, we are loading. We are loading. So the body is called okay, that is terrible. That is terrible. Okay, whatever. 41, and let me remember the name. I think my camera broke. One moment. I need to reset it. camera is fixed. And the microcontroller is CPU. So the body is called, okay, UFQ FPN 48, sure. This one, okay, and how do I see if there are more ADCs? Let's open like the beefiest one in the same body. Because the right side of this selector is not useful, and the left side as well. I have only one column and ADCs. 3 ADCs. Wait, am I a dumbass? Wait a second. Hold on a minute. Am I a dumbass? Hello, internet? ADC. 2 ADCs. So there is in the same body. And what is the price? Just for my curiosity. Sample and buy. 3.4, but the price will be inflated outside of their website, and it's also a price for 1000 units. Let's see. 2.2. Let's check DigiKey. One moment. Googling. digikey.com. So 31, let's say RB8. RB. Wait, not RB, right? CBU. I'm dumbass. CBU. And the price, they're out of stock, okay. $5 per one. Okay. But why 200? Okay, $5, sure. $5 and out of stock. And the second one is called, I can buy the cheapest one of them, and the cheapest one is CC. Okay. $5 there and $5 here. No way. That's an awkward situation. That's very awkward. Okay, let's say I will buy 10, 3.8. That is not that much more expensive, actually. Why shouldn't I use it then? It's a very good question, Negorsa. I just not sure why. Maybe actually when I was designing this board, these versions were not that yet released, but I don't think so. I'm not sure. I think G4 is like quite not old, but is already well-established family. Yes, for sure. At least for your for a project like this, which is like relatively high end, it is much better to not hack things in software, but have hardware help you as much as it can without removing control from you. Like, you should be able to control things, but like I don't really want to manually switch when I measure what. So like it's a very good update. Maybe in production, if it was like something production wise, and like I had specific parameters, like I don't know, the number of PCBs we need to manufacture and the exact application, like how important is our current measurement, it could have changed. The opinion could have changed. By in this particular example, I'd say that it is 100% worth it. And I actually maybe order some of them. If you want, we can do a soldering stream when I will be like either soldering a new controller or just changing the MCU on one of the assembled ones. but maybe like later. So now I actually now have a question. I would also like to open a datasheet. 4.9. No. I want reference manual. Because I think there is also a flash issue we need to be aware of. And it will be here. One moment. I remember it being somewhere here. No. Not here. Oh, here it is. Okay, so it is a category 4 device, which means it's the Flash implementation sucks ass. Damn. And why does it suck ass? If a single bank, which compared to this is dual bank, but it's also, oh, sorry, my bad. Where was I? I was in the end of this chapter. Yes, here. It's category 2 with category 4. Let's open a new one to not forget it. Close. Hold on, close. And here, category 4. Up to 128 single bank. And here, let's say category 4. Let's compare. No, it actually looks quite the same. And single bank is useful. Like, I don't lose anything by just having more memory in a single bank. So it's fine. Then I should definitely try to upgrade because it will solve so many issues. Not so many issues, but it will solve like a big one, which is measurement of like voltage, bus voltage, and temperature, while not affecting the phase currents at all, which is very useful. So I will know it for myself as well. One moment. You ask very good quality questions, Negversus. Thank you very much. Like, it helps a lot to think. Noting. I will also read about this MCU outside of stream, just to make sure that it's compatible. Fully, it should be. Like, they have high compatibility between MCUs in a single family, but just in case, to not order like $50 of microcontrollers that will not work, I need to check it out first. So now that this question is solved for now, let's get back to checking our ADC example. One moment, I need to fill myself some water. All right, water refilled. Chat said you can go up to 5. Yes, you can. We saw it on the website, but I believe, maybe I'm wrong again. I was wrong multiple times today, so might as well be again. Let's check it, but I believe that the ones that have 5 ADCs don't have the body I need, like the case I need. So, no, I'm a dumbass. They do have 5 ADCs here and 48 UFQFPN. Yes, this is the correct one. Okay, let's check the price. Why not? Given that we are at it as well, we might as well check it. So let's say this. Let's say we will take the cheapest one, and the cheapest will be the one with least memory. And I don't need much memory because I am over optimizing anything anywhere anyway. Which is a terrible habit, but I have it. And let's say, nope, not like this. Actually, do you like it? I just made this connector so that I can do like things like this. And like show off things if people have questions. And let's see, this is not the correct one, this is the correct one. And this one, okay. It is more expensive than this one with 3, but not that much more expensive. Like it's almost not expensive, not more expensive at all. Okay, but it has a bit less flash, which is fine. I don't need it anyways. And let's check the memory as a flash type. And it was G473, which is type 3, category 3, and category 3 is dual bank. Oh, I'm a dumbass. I was doing the doing the search while not showing it to you. I'm sorry. Actually, Nick Versa, you know what? The microcontroller with 5 ADCs, that is this one, in the same body, also has 2 flash pages, separate ones, and this is very useful. And very useful because in such configuration, you can write a bootloader very effectively. You can use one flashbang for your main firmware and one for bootloader, and it's very easy to manage because you don't need to like do too much hassle with your linker scripts. So actually, now that you forced me to face reality and Google options of STM32G4 microcontrollers, I would say that I will try to upgrade actually to the one with 5 ADCs. And I don't need 5, I only need 3. But having 2 flashbangs will be very useful for future. And maybe we will do a stream with me developing, like multiple streams with me developing bootloaders. Also, we would like to see a stream developing bootloaders. Like, bootloaders are a very tough task to do. I did it once for SPI bootloader with custom protocol. It was not a pain in the ass, it took like 3 days, but it was quite a bit of work. But yeah, if people would like to see it, I will definitely do it on stream, because why not? At least like this raw dog stream today, it wasn't planned, goes very nicely Like you give a very great feedback, and I'm just chilling here, listening to music, reading documentation. I'm quite fine with this. Okay, so let me note this MCU for myself as well for later review out of stream. Check this MCU. I do have to. What do you mean updates with encryption? You mean firmware encryption in bootloader? Or something else? Let me see. Do you think I should go for like the crypto encrypted one? Because I have no idea what IES 256 means. I'm not sure if it's firmware related or something else. So I will also Google it, like learn it off stream. So it is bootloader related. Okay. Okay, noting for myself. Okay, if you're interested, we might as well try to go for the version of this scripter hasher, whatever this thing is, and try to make a bootloader that uses it on stream. Why not? But I will probably read up about it off stream so that I'm not reading documentation on stream fully, because it will be embarrassing and probably very boring. So I would come prepared just without any code written, or at least any production code written. One moment, noting. Note done. Okay, quite a few notes after today's stream. And quite a few finds. Should I be worried about anything else? I don't think so. At least for now. It should be alright. Let's close it. And let's get back to ADCs. Actually, now, now that you told me about it, I'm already thinking about how to do it properly, and I have no intentions. Like, I have very low motivation to do examples that does it wrong in the wrong way. And I think that I will just forget completely about anything but the main ADCs that are used for current sensors, because they will stay the same for the new microcontroller as well. And we will implement other measurements like voltage and temperature when we get a new MCU to install on the board. And I also will need to think, if people want a soldering stream, how to set it up, because I'm not sure exactly. I'm too shy, I'm not ready to show my face. But we will figure it out. Okay, let's keep going. Okay. This sounds like it doesn't exist. And I would imagine that it's supposed to be EDC2, get pointer, and check the channels. All right. And let me remember how I did it before. Oh, I do remember now how I did it. Oh, now I remember. And how it is done. Oh no, this is awful. Oh. Okay, I do remember now. So how it is done now is that, let me get back to the drawing board. Oh my. Right now, like, this is a perfect situation we would like. And the actual situation is a bit different. It is like, this is the time and our period. Oh. And what we do is we measure current for as long as we can. For as long as we can mathematically, when we multiply all the constants and all the multipliers of time, and like time is quite rough to align. It is quite rough to align time to the microcontroller frequency for ADCs and STM32, so we can't do it perfectly. So let's assume this is the time, and I measure currents, like I, let's say, I phase. And then in the same measurement call, I just spend some time measuring. On one channel, I measure voltage, and on the other channel, I measure temperature. What letter to use for temperature? Because let's say temp. Okay, this is usable, but the problem with this is that there is no good way, not a good way, but no good reason to measure voltage like 20,000 times per second. Like, it is insanely unreasonable, especially without proper front end. And by front end, I mean like a operational amplifier and things like this, which I don't have. So I just waste my ADC cycles on measuring voltage and temperature. And that's fine, I guess, for now. But with a new microcontroller, it can be moved to a different location, to a different ADC, which will measure them not like 20k times per second, but I'd say like 100 times per second will be more than enough. And for temperature, it can be even lower, but given that it will most likely be the same ADC, it might as well be like together. But otherwise, if I will use a separate ADC for both voltage and temperature, I will be like too how to call myself in this situation. Like, I'm not sure, like too rich, too picky, too demanding, not sure. But I just think it's not the best idea we can have. So now that I remember how it works, let's keep it as is, I guess, for now. So, oh, okay. We disable one phase because I think I was measuring current in this test using DC load, which I have on my desk, like here. It's a DC load to measure things, but not today. Maybe next stream or like a stream after, we can use a DC load to measure and calibrate our current sensors. But not now. So, well, let's continue working on the test. Okay. 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 This function is also not implemented. How long ago did I write this example? Hello? Are they actually not implemented? Did I change it? I don't remember. No, this is the wrong way. Let's find. Search. Yep, the only place. Okay, that's awkward. Temperature and voltage. Okay, and how is it supposed to be working now? We only have 5 functions, like 6. We wait for... Okay. Oh. Okay, so it's actually very easy to solve. Start sampling. So I have functions to start sampling separately for a channel. What? Where is it implemented? Oh no! Hold on a second. Oh no! This function doesn't have a declaration in H file. Okay, this is a mess. This is definitely a mess. Let me test it. So static function. Okay, all right. These functions supposed to be either static inline or globally available. I do believe they're genuinely useless, though. Let's just remove them. Who needs them? So let's remove this, start sampling, and then fix the waiting cycle. Wait for conversion, sure, the same for ADC2. Now we'll explain why we need two separate functions, maybe later. It's also quite an interesting reason. And here we have our pointers, sounds good. We'll measure the values. I can also explain why we work with pointers also later. But for now, let's first make sure it works. So phase A, okay. Phase B, okay. Coding calculation, assuming no error sampling. These values, all of these values are supposed to be constants of source or definitions. So let's note it. Later, so this is current measurement. Temperature so data conversion, okay, I think I was lazy. We will need to fix it later. And what is this? This is a bus voltage. Okay, sure, looks good to me. And this constant is not great. Much better. Let's actually test it. I think it should be all right. At least we can change the voltage on our power supply and see if it changes the actual voltage we see on the microcontroller. So this is example, it's called example 5, but actually let's copy the body into example 7. Let's leave it here commented out. Let's edit here. And let's flash it. Example 7. Build. Make sure we don't have too many errors. And where are my errors views? Did I close it? Hello? Where did it go? Oh, I see. Oh, it actually builds first time. Hello? Let's test it. So now, what do we supposed to see? This variable. And we're supposed to see... Oh shit, oh crap, oh, what's happening? Oh, oh no, this is terrible, oh no. Okay, I almost exploded my motor because I just said whatever, let's put all the voltage I have into one of the phases to measure it. And it is fine, for example, when we calibrate the current sensors using DC load, but it is not fine where actual motor, like small motor, is touched, because this is a small motor. I have much bigger motor, like let me show you how big of a motor I have. Like that is a big boy. I'd say that motor control engineering is a good supplementation for gym because you need to carry motors that weight like 15 kilograms. Highly recommend. So now, that was a terrible idea, and now I need to fix it. And to do so, I need to lower my current limit so that I don't fire off my motor. And fix the code. No. Like, it's not a huge motor per se. Like, there are motors that are like gigawatts in like wind turbines, but it's quite a heavy motor for like a person, individual to have and to work with. This is like around the dangerous territory of not using 48 volts. I'd say this motor I showed is right around the limit after which you need more than 48 volts, and 48 volts is the safe standard when you don't need to be certified to work with the voltages, like to develop the electronics for such voltages. Like 48 volts is still safe to work with. Okay. Let's fix it. I don't think I actually need this at all for this example. Don't need. Yes, they can. Actually, if you want the next stream, I can prepare a board that this motor will be attached to, and it will spin quite fine. Because these MOSFETs, if I remember my calculations correctly from a year ago, can drive up to 400 watts when working in FOC. So 400 watts is quite a lot, and quite big motors can be rotated with this pretty well. But I don't think I can, at least for now, run FOC on it because I need to install the encoder. Like the encoder I use, because I use custom encoder. Like this one, this small, tiny guy. Where is it? Show it. Like such a tiny guy. And I will need to upgrade the motor first before I can test FOC on it. But it's possible. Like I can definitely rotate it in the open loop configuration when I don't measure anything. It will spin nicely, and I did test it before. So I can confirm. As of for now, remove all of it. This and that would go right. Let's save our motor from overheating. Let's turn it on. It's going like crazy. Let's flash it. MOSFETs are actually quite impressive these days. They have such a low resistance that they can drive quite insane currents. Okay. Something is broken. Okay, it's fixed now. We're safe, we're safe. Now let's see if our currents are as expected. This shows about 14, which is correct because the current measurement we are doing is middle point, because we would like to measure both positive and negative currents, and we can do it up to 15 amps, and 15 is a middle point I don't remove, I believe, so it shows an actual correct value. Yes, so let's actually subtract it so that we can show an actual value we measure. And this actual value we measure can be used for calibration. So it was good to me. It was good to me as well. Let's try again. I actually have quite a lot of troubles with ADCs. Like, I have noted in my things to do for a very long time to actually learn how to properly work with ADCs. And there is quite a well-designed course from Texas Instruments about ADCs. I just never found like strength to just sit and watch it. And I think like maybe I should do it on stream, learning ADCs from scratch. But I think it will be rather boring for people to also just watch videos about ADCs with me. So let's see. Okay, so we have roughly 80 milliamps of error, 80 to 90, okay. But our voltage is not measured. Why? Why is our voltage not measured? Is the voltage value here? Okay. Here it's empty, and this one is also empty. All right. Where is the setup code? GPIOs, we set up 2 for both channels. That is correct. All right. Sure. 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 Oh, we don't set it up here. Okay, okay. And why? Okay, I think I already done what I said I need to do, is that I only measure the currents. I don't measure anything else in the current NDC setup. Which is fine, I guess. This is exactly what we wanted, but we need to remove those from this example because this is misleading this time. Okay. So let's fix the styling a bit. Okay, this looks fine, this looks fine. This looks all right, and I think that this is a very nice test to show how to use ADCs. Okay. It is functional now. This is a proper note I will do later. Low delay. Looks good to me. At least for now. I will need to note that I need to add description and constants. So I move here. Oh, so you never learned how to use ADCs? So your experiment with RISC-V are your first microcontroller work? So you haven't worked with microcontrollers before? I will need to check the Texas Instruments, like, how do I call it? Like, if I'm allowed to stream their courses, because they're free. So if they're free, I would imagine that I can stream them. I just need to make sure that I actually can. Okay, and note. Oh, so this is not what you do for a living then, I see. Are you programming for a living something else, or like do something outside of programming? G0 is a good family to work with. I worked with G0. I had one nice board. Like one of my first PCBs for motor controller was on G0. Okay, so bring up AC. hobbies, I see. That's quite a nice hobby to have, actually. Why not? DAC should be very simple. Let's just implement it. Okay. I do believe that in DAC we only have like 2 functions or 3 functions available. Yep, only 3. This I can add to every example. Also, I hate the names of these examples. Or do I? No, they're fine. Or are they? I will rename them later. I don't like the names, but that's all right for now. This doesn't change the code functionality at all. So we set it up, and I need an example on how I use it properly. An example from myself from a week ago. So set up DAC and just run the number. And to test DAC, we will need to turn on our oscilloscope. Let's do it. It will take quite a while to boot, so we might as well wait for it. Wait for it and keep writing the code. So let's do a dummy delay. Now let's do it 10 milliseconds, so as we have more values to work with. And here we will use DAC, outset value F32. So the value we will need to figure out, then the upper limit we will set as 1 and -1, because we will use a sine function. So let's say static float angle, test angle equals to 0. Actually, it will be exactly the same as here, with just different frequency. Let's say it will be like this. And like that. And we will use the angle, which we didn't define. This is not needed. Frequency, angle increment. Actually, yeah, let's do it. Why not? And now we need angle as well. So we needed that, and this, and that, and this, and float angle. Static float though. Current angle equals to 0. So current angle will go here. And after this function is called, we need to update the angle. Current angle plus our increment. Okay, should be fine. We set the value, we wait, we rock. So now we need to attach our oscilloscope to a specialized connector we have on the PCB. Just here, and I see nothing because of the camera. I'm sorry. Okay, hello. Now much better. Nice. So we are attached, and let's set it up. So channel 1 is not what we need channel 4. Okay, move it down. I think I need to connect the oscilloscope to my PC and stream the oscilloscope screen, because like I'm not sure it's seen nicely. I hope it is decent enough. So we need to change scale. That sounds reasonable. And also the waveform type acquisition, this and that, and roll, and fine, and menu off. Perfect. And now we need to flash and test. Okay, test 8. Let's roll. Let's see. Please don't pay attention to the dust on my table. Okay, it's very unequal, uneven. This should be better. Okay, let's run. Okay, this is awful. It doesn't work as expected. I think, oh, I'm an idiot. I'm such a dumbass. Okay. My bad. Okay. So this is hella wrong. Let's fix it. Of course it doesn't work. How would it supposed to work if I don't apply a sine function? Angle increment, and I need to calculate it like this, and it will be float sine value equals to arm sine f32 of our current angle, and I need to set it here. That should work fine. Let's test it again. Flashing, standby, elevator music. Now we are ready. Let's go. Nice. But that looks rather odd. I think it looks rather odd because of the frequency we output. Okay, that's fine. That works. Works for me. So let's see. How are we looking? Current angle, RPS target. Actually, can I run it slower? I can. Can I run it faster though? I can't. Can I change the view? I'm a bit curious. One moment, I'm sorry. Acquisition. YT. Menu off. Trigger. Trigger and time. Okay, hello. Okay. Okay. Okay, and it triggers 2 times per period, which I don't like. Sure, let's change it. Edge, type edge, rising. Okay, but it's supposed to be triggering only once. Right? Rising, rising, rising. Let's see. Oh, because it's supposed to be channel 4. Now that's much better. Or is it? It is not! Where is my trigger? Now it's done. Okay. Now that looks much better. Okay. So yes, it looks a bit jumpy because of the frequency we output DAC with, but it's fine. It's totally fine. Not a big deal at all. So let's, oh, my bad. Let's go to the acquisition, roll again, menu off. Looks good to me. So DAC test is implemented. Let's make a comment that I need to document it. Okay, looks good. I think this should be called hertz, so it's easier to read, and hertz here as well. Otherwise, it is confusing what this value means. Angle increment, it should be radians, also confusing. Radians per second, actually. Confusing names are bad names. Fixed, now it's much better. And here should be current angular radians. No, it should be radians. Also, my bad. Okay, current angular radians, and radians here should be all right. And this example, radians, write proper variable names, guys. Let's test it again just to make sure it works. Okay, it doesn't build. Makes sense. Let's try again. Let's run. Yep, works like charm. So now, let's go back. This example is ready. What is the next example? Breakup. Oh, brake resistor is a pain in the butt. I had to actually redesign the PCB 3 times to add the brake resistor functionality, because brake resistor for big motors is incredibly important, because motors do not know how to stop when you spin them. Like, Newton law is quite punishing because when you put a lot of energy to spin something up, you have to put a lot of energy to slow it down. Like, it works this way. And brake resistors are like designed specifically so that you can take the energy from the motor, like electrical energy, convert it to thermal energy so that it dissipates and your motor stops faster. And stops not only faster, but in a controlled way. And it was actually very confusing to me at first. It's kind of confusing to me still. But yeah, I had to redesign a board 2 times to add like a small circuit to implement the brake resistor functionality. But I haven't tested it yet at all. So this is something we will implement on stream later, like from scratch, because like I actually didn't do it, like haven't done it before at all. So we will not implement it now because I'm not at a brain capacity to do it now. So let's see what else we have. This we cannot test right now. And CAN bus we cannot test right now as well. And it's actually all we could have implemented. Is it actually all? Let's actually stop our oscilloscope. Now let's remove the probe. Actually, let's remove the power first. Then remove the probe. Okay, it's stuck. Step bro, I'm stuck. Sure. Looks better. Now we are back. Let's put the power on. Let's start spinning. And for that we need to change example to 6 and flash. And after that we will need to look through the old code. I need to clean up. Now run. We spin. Light sucks. That's better. We implemented that, and we implemented that. we cannot implement that yet. We cannot test this, and we cannot implement that yet, as well as this. This looks fine. So now, what else? What else? What else? What else? Let's go to the better view. Now let's go and test my, not test, but clean my old code from examples, because why not? Today is a chill stream after all. Or is it quite a big description? I will save it around here and rewrite it later. Probably very useful, but needs right. So let's remove this code. Okay, what else do we have? We have toggle free GPIO, that is useless. Toggle DC, this is useless. Essential smart rotation with proper voltage forming. This is implemented today, which is useless, but descriptions can be useful. Let's save description, it's probably useful. To example 6. To do probably useful, but needs a rewrite. Okay, what else do we have here? Note count. Oh, I can play music on my motor. Actually, I would like to test it because I do remember implementing this. And PMSM motors can be used to play motors or to play music. I actually did it. It was a task for my job. Like, don't ask what my client was, but like the task was to implement a sequence that would play small music at device starts up using the motor integrated into the device. So I was testing it on my own project. And it's actually a functional code. I just need to make sure it works with our updated function names and stuff, and let's see if it works. But I also believe I will not be able to show you the sound. Let's actually check it. We might as well check it if it works at first, and then if you can hear it. So that is not needed. Fine. Sure. Fine. It should be actually fully functional as is. So let's try to run it. I actually am very curious if the music will play. Okay. So let's go to main. I don't think it has a way to run it from here. So let's actually hard code it. Let's say, I don't know, example 12. Because no. Let's comment it out. You've seen nothing. Example 11. Make some noise. Such a nice function name. Okay. Here, let's run it. Okay. Let me remove my headphones to see it, to hear it actually. So let's see. And it works! Did you hear it? Can you hear it? It's not very loud. Let me actually try to make it louder. It works! Such a nice thing. Okay, yeah. Let's turn off the music. Sure, this is correct. And let me actually put my microphone to it. Wait a second. I need more current. Okay. It is not loud enough. Let me fix it. Let me fix it. And not loud enough. Can I? One moment. Can you hear me? Actually, you can. So yes, let me fix the volume. Let's try to make it louder. And how do we make it louder? We just push more voltage through it. Now let's see, let's see. So where is the function? Where is the function? How much voltage do we push? We push 6 volts. We can push up to 12. Sure. 12 volts, 12 volts, 12 volts. Let's see if it will be louder. Do I have 6 anywhere else? I don't think so. Let's test, let's test. Okay. It is definitely louder. Let me put microphone closer. No. Let me actually remove my filters from my microphone completely because I think they are blocking the sound. Can I remove it without breaking anything? Let's see. You should have heard it. Did you hear it? Oh, this is so fun. Did you hear it? Were you able to? Did it sound well? Did it sound nice? I know it's such a silly thing, but I'm so proud of myself to for doing it. True. Very true, very true. We are both old enough to know what's not. Okay. Very true. Let me put my filters back so that you will not hear my squeaky chair and my heavy breathing. Okay, we're fine. Okay, sound playing is an example I would definitely want to preserve and put into a separate example. Let's get back the music. Let's get back the motor. Let's get back the spinning. And our spinning is example 6. Let's comment it out. Let's flash. All right, let's see what else we have in our examples. Count poles. This is also a very useful example because we do need to know how many poles on the motor we have. And if we don't have documentation, we can actually count it by using our hardware. But I will need to reread this code later. What else? Align encoder to motor. Okay, this looks like a chaos. But it's functional chaos. But it's also already implemented in a separate function. Let me check it. Because I already did implement the new way of doing this, which is almost exactly the same, but still. Let me see. Okay, align the motor to shaft. Yep. This can be removed, and this, and that, and this. And what do we have in the function itself? As a setup, we don't need. And here it is mostly the same. Raw estimation of the alignment angle. Okay, it's the same. Second alignment, save data to a variable. Move a bit to the center. Okay. And what else? Situation when one measurement is very close to encoder max. Okay, it is useless because I already moved it to two separate functions that implement separate behaviors from this. But the comment is also useless because both functions are... Oh no! Oh no! Wait a second, this function doesn't have a comment. Let's see it to do. Okay. Do and no. Okay, explanation or description of the function. And move this comment up. Probably useful, but needs rewriting. All right, now we can remove it safely. So, should we read this function? Or should we convert the music playing into a better example? Because right now it's kind of hacky. And maybe like chat has music ideas they would like me to play on my motor. I'm taking requests. Maybe we can play like the sound would be one note at a time, but we can play like whatever. Maybe next stream I can prepare like a proper converter from like the song to notes the motor can play, and we can play some songs. It would be quite fun. All right. This is actually incorrect, I would imagine. Or is it? No, I don't think it is. Okay. So let's actually read the counting poles function. This is not needed. Let's actually test it first, but first we need to fix it. So correct. Looks fine. Also fine. That's a bit too much. Fine. Okay. Our first estimate is a single pole pair, which is fine. Here, angle. And the code to do it, which we will read after we test it. So let's do it. Let's hack the motor again. Okay. 12. And this is example, it's actually 12. Example 12, count motor pole pairs. Let's flash it and test it if it counts the pole pairs correctly. Okay, and you people who watch me and don't follow me please. I will appreciate it a lot. It will help me a lot, so let's flash it. Okay. And run, and we should see a full rotation of the motor. And then it stops, and then we need to see our estimate. Let's check it. And it should be somewhere in left expressions. And let's see what we need to look at to see the pole or pairs count. It is saved to F32. What happened? So it estimates 4 pole pairs and it should round it, right? In U32, yes, it says 4 pole pairs, which is correct. My motor has 4 pole pairs indeed. Okay. This is also okay. Okay, let's change the perspective because I can't see stuff. Okay, and how does the code works and how does it save? Pole pairs estimate. Okay. Sure. Okay, yes. So the code works fine. It's measured that we have 4 pole pairs. It's actually a very useful test for any kind of motor that can be spinned by my driver. So let's actually review the code, clean the mess, and save it as a separate example. It is a separate example, but it's a separate example according to the new system. So change the styling a bit. This is fine now. This is also fine. Current electrical angle, sure. Current shaft angle, sure. Previous shaft angle, sure. And current system angle, sure. Line the motor shaft to starting no angle. Sounds fine. We might as well use more volts, because why not? This will work for a bigger motor just fine. Also, no, I'd say 3 is enough, because bigger motors always, not always, but usually have smaller resistance actually. No, sometimes they have bigger, sometimes they have smaller, and like putting too many volts into such function can lead to us burning the motor the same way we did like an hour ago, where I had to like fast click off my power supply because it was like sending amp and a half just through a single phase. Let's not be dumb and let's not do this again. 3 volts is fine. Let's switch it to the better readable constant. Okay, we read the initial position of the encoder after we aligned. So, okay. After we are aligned to a phase, whichever it is, we read the initial encoder value. It doesn't matter what pole pair it is, it doesn't matter what pole it is, it just matters that it is a known position that is aligned to the pole pair. So then previous shaft angle is current shaft angle because we are in starting, that's fine. Sure. This is a debug only. Yep, comment says that. But why do I do this twice? That's confusing. Isn't it like the same line? Am I tripping? It is the same line. Why am I doing this? It is the same line throughout. Okay, what? That's confusing, but fine. I hope it will not break. I'm very confused, but let's see. Let's test it again. Actually, because like, who knows? Maybe I broke something. Then, okay, and if estimate was made, let's run it. Run. We need to see a full revolution. And we see the estimate of 4 pole pairs, which is right. Okay. I didn't broke anything. Let's go back. Didn't break anything. So here an estimation was made and half was encoder built. But I already have this as a constant, which can be switched to middle point. Counts, switch. This is a better style. Let's remove this. It will make code more readable. Get current angle. Looks fine. Current angle bits. Sure. Okay, this whole thing is actually the same we implemented for proper current count measurements, and I think we should actually change it into a function we know it will be much better. I will add to do because there is a lot of code here and it's kind of confusing before you start reading it. It's already inside a function somewhere. Switch it to a function. What temp you measured in ADC? Is it from internal NTC inside motor coil or something on the board to protect it? It is on the board. It is IC from Texas Instruments that is supposed to measure temperature around the MOSFET area. Having a temperature measurement inside the motor would be very nice and very helpful. But my motors don't have any attachments for this. And also I don't have... Actually, this is... Now that we've changed the controller, it's a very interesting topic for discussion because I do believe, I'm not sure, but I do believe that I did not add any connectors to measure like temperature from inside the motor, even though it's a good idea, because I simply hadn't had like ADCs, enough ADCs to do it. Because my idea was that I will measure one phase and one other current source with each ADC, and that's all. That's all I have time for. And now that I will have more ADCs, I can actually use more pins on my microcontroller to measure other stuff. I just not sure if I have any pins available, because I believe we can actually check the schematic that I use almost everything microcontroller have to offer. So let's see if I actually have any spare pins with ADC support. So I do have PA2 and PA3, and they are most likely are ADCs. So it is possible that I can add a connector to the PCB to add an external temperature sensor that can be inside the coils, and it will be actually very useful. I would imagine that this is a very nice idea. Actually, there might as well be another stream when I will be redesigning the board, because the current iteration is 3, it's i3. So like wait for a PCB improvement iteration when we actually will probably add this idea. I will know it for myself because like this is a good one. Do I have to-dos inside the schematic? I don't believe I do. I don't believe I do because I think I solved all the previous to-dos and hadn't had any new ones. Okay, let me know it. Note to self. When redesigning the motor controller, which is M1E2, add connectors to touch external temperature sensors. That's going to be very useful for the future. Because when you are done with FOC implementation and you are confident in your like current vector forming and your voltage vector forming, in your feedback from an encoder, when your control loops are running, the main limiting factor you have to work with is actually motor temperature. So the suggestion is very nice, and it's currently not supported by the PCB in the way it is implemented now. Okay, so let's keep reading the code. Let's keep reading the function because we are almost there. Okay, this is fine. Sure. I haven't. Okay, this is fine. Initial angle difference. Initial angle difference. Okay. To finish one full shaft resolution, we need to be close to where we mechanically started, and we need to make at least one electrical angle. One electrical rotation for better resolution. Revolution, actually. Damn, my English sucks. Don't judge me. Don't judge me. Okay, initial angle difference. That is a terrible constant. I don't like it at all. Okay, so to do, change constants into a proper definitions or constant variables. Okay. But what it means is that the difference should be almost 0, which means that we made almost the whole revolution. Okay, and electrical angle should be at least one revolution, which is fine. Current electrical angle, okay. Estimation is made is 0, which is by default. And if electrical revolution is more than at least one turn, estimation was made is fine. Counts per revolution. Initial angle difference. I'm a bit confused by this line. Counts per revolution, okay. We divide by initial angle. That's all right. That's confusing as hell, actually. No, it is not. It is not because we just... Yes, this is correct. So what we have here is we have a full revolution of the encoder, which is like 2 in the power of 21. And we divide it by whatever the... like the current angle we've run to. No, it's still confusing. What the hell? What does this value even stores? F32. I'm confused what this does. If you're also confused by reading your own code, type 1 in the chat. Okay. It's initial angle bits, which we read here. Yes. Current shaft angle bits. Correct. This is also correct. Okay. So by the end of the rotation, it is supposed to be like maximum value. I'm so confused. I think my brain isn't working properly on stream. I'm so sorry. Like, it works fine, but I don't know why. And I don't know why. Initial angle. Okay, I will figure it out later off stream. It will be much better idea. Round F. Okay. Round F is the right function to use. Current electrical angle. This is very easy to understand because it's just divides current electrical angle by 2 pi. which gives us number of revolutions. Okay. And this is, to better understand this value, we need to forcefully convert it. It will be read much better. So because this is a floating point value and we convert it to int value after rounding. Sounds good to me. We stop the motor. So the only confusing part is like a single line, this one. Other than this line, everything else looks absolutely fine to me. Nice and dandy. So now, how do we put it as an example? Because it is actually a production useful function. But it might as well be a bring up function, because why not? We removed all of those. We removed this. And those are present still, okay? So let's add another bring up function. Count motor all pairs void, and it's supposed to have a number. Let's add it to the main right away. Leaf example number 12. We call this function just without this part. Okay, looks good to me. Let's go back and implement it. We can actually just rename it. Sounds absolutely fine as is. Like this, and the comment do right. Definitely useful, but may need adjustment. And let's move it to a correct location inside the file. Correct location, which is here. As for playing the music, it is definitely not a bring up. It is not something you would test your PCB for. So I think it should be moved to somewhere else. But where? Where is quite a confusing part. Not sure for now. Let's just add a comment to move it out. Do right. Definitely the right description. Definitely useful, but may need some adjustment. Okay. And another to do. Move the function to the place where it will make more sense. Okay. So let's go to this file. This is removed. This is removed, and this is the only function I will need to clean up, and I just don't have brain cells activated to do so. Don't have enough of them. I think it was very successful. I implemented quite a few examples today. We found quite an interesting flex for forcing ourselves to use only floats inside the code, which is thanks Nick Versa for this. This was an off-schedule stream, which went really well. I think it is all for today. Thanks everyone for watching, and don't forget to follow if you want, and also follow if you don't want. I will appreciate it a lot. See you on the next one.